In this video, we'll look at finding distances from a point to a line and from a point to a plane. In the process, we'll look at equations of lines and planes in three-dimensional space, and we'll see that these are applications of the dot product and the cross product. Okay, and so the first thing that I'll do is this question: given the vector equation for a line, r of t equal the vector 3, 4, negative 1 plus vector negative 2, 5, 1 times the parameter t, given that line specified by that equation, actually it's a vector valued function, but it defines a line. Given that line, find the distance from the line to the point 3, 2, 4. And you can see a picture of that line and point there graphed, and I just puts a lot of time in figuring out how to do this on Mathematica, so this is encoding the line in Mathematica, and the point, there's the point 3, 2, 4, and this specifies this is the parametric form for the line. I'll get to that in a minute, but I just put that time into figuring out how to do it, and I wanted to be able to visualize this spinning this thing around. Whoa. And so there, that was fun. That's what we're going to try to do, calculate the distance from this point to the line. So let's take a look at this picture again, and I'll talk just a little bit about this way of expressing the line. What I'm looking at here is the 3, 4, negative 1 is a vector that you can see right here as a position vector that's locating a point. Then I'm using parentheses 3, 4, negative 1 to indicate that point. So that point would be right there. And then this negative 2, 5, 1 is another vector that you can see here parallel to the line. And this parameter t is some scalar multiple that can make it 1 times the vector, or 2 times the length, or 3 times, or a half, or a negative 1 time, or negative 3 times, etc. So it always produces some parallel vector to whatever line we might be working with. So this is a direction vector. So then there's the vector r, which is this dotted one, that's actually like a position vector locating points that are on the line. So as we change the parameter, we get longer and shorter and opposite direction parallel vectors that trace out the line, that follow the direction of the line, but then it's actually r that I would maybe say more specifically traces out the line. Suppose that we had a parameter of 2, then suddenly what happens is this vector here becomes twice as long, and so r would be the sum of these two vectors, and it traces out to that point. So we could determine all the points on the line by expressing the vector in this form. Now that's not the only way to write the line. It's important to see other versions of the way to express the line. So let's get this stuff out of here for a minute. Given the line written in this form, I can also write the parametric form, and the parametric form would say each of the components, x, can be determined by this fixed value 3 and then negative 2 times t. The y value is given by the 4 plus 5t. The z value, this would be x, y, and z for any point on the line. As you can see that, when you add these two vectors together, you're going to come up with this expression. You'll have negative 1 plus t. In other words, maybe I could have done that. What does it actually look like if you actually added them together? It would look like 3 minus 2t and 4 plus 5t and negative 1 plus t. And so there you can see where I'm getting x, where I'm getting the y value, where the z value comes from in this parametric form. And then lastly, there's one other form that's an important one to recognize. I could solve each of these equations for the parameter t, and then because it is the same parameter in each of these values, set each of those results equal. So what I mean is you could get x minus 3 divided by negative 2 when you solve for t equals, and when I solve for t in this one, I'll have y minus 4 divided by 5, and when I solve for t in this one, I'll get z plus 1. So this is called the symmetric form. I could say that I have direction numbers that I can actually read off by looking at this symmetric form. Negative 2, b equal 5, c equal 1, and it's, if I had it in symmetric form, the a, b, and c are the components of a direction vector. The direction vector is the vector that's parallel to the line. That it's identified here as components of these equations. The negative 2, 5, and the 1 form the direction vector. It's the same direction vector that I saw back right here. Okay, all of that was really just to talk about the different ways of expressing the equation of the line in three-dimensional space. Oh yeah, I want to say one other thing. It's possible that the A or the B or the C might be 0, and in the case that one of them is 0, you won't see it in exactly this form, because if one of those components of the direction vector is 0, you'll have to just have a constant, so you'll end up with a comma and then a constant for one of these three parts. So look for that in some of the examples. That happens sometimes. Alright, so we'll go back and see if we can actually answer the question, understanding how the line is expressed, identifying a point that we want to find a distance to. So we'll look at it like this. Alright, so I've got this point Q and some other point P that I know is on the line. And I think I'm going to put that point down here. As I started thinking about how I'm going to draw it, it'll be easier for me to put it here. It could be anywhere, any point on the line. All you need, the point that I'm choosing, 3, 4, negative 1, comes from a parameter value of 0, right? So it's when t is 0, you could use any t value and get any point on the line, but I'm using this point and I'm drawing it here just because I think my picture will go smoother for me. I'm using parentheses again, right, for that point. Now, I want to find the distance, and so to find the distance from the point to the line, I have to imagine a perpendicular, because that is the shortest distance, and that would be the actual distance, the shortest distance to the line. So now to draw that and make it perpendicular, it really kind of depends on your perspective in the three-dimensional space. I might draw it so that it really does look perpendicular in two-dimensional space as well. So this is the distance that this whole question is centered around. What exactly is that distance? In order to find that, I'm going to do a cross product. And what I want to do here, part of the video, is to explain the formula and the background and really derive it. You wouldn't have to do this in every calculation, right? You can go right to the formula. But I'm trying to put in the formula a derivation of where the formula comes from. So what I'm like to imagine here is that I've got this sort of like a high wire that I'm going to be balancing on and doing trigonometry in three-dimensional space, balancing on this high wire, right? So I'm going to imagine this vector PQ, and therefore I can now see this triangle that I can do right triangle trigonometry in this triangle, balanced in three-dimensional space on this high wire. So how are we going to do it? We're going to find D once we've identified this vector PQ, and we can identify a vector V that's a direction vector for the line. So I'll just put it here. This is V. You know, it really doesn't matter how long or short I actually draw that. I need this direction vector V, I need this vector PQ, and from that I have a triangle that I can use to find the distance D. Where it begins is the angle between these vectors, theta, and the trigonometry that the sine of theta is that opposite side, d, divided by the hypotenuse, which is the magnitude of vector PQ. From that, I can solve for d. I can write the distance is the magnitude of vector PQ times the sine of theta. And if I actually knew the angle between the two vectors, I could just use that and calculate the distance right there. But often we wouldn't have the angle. Instead, we might just have information to find the direction vector and the vector PQ. So the trick that we do here is we can multiply the top and the bottom by the magnitude of v, because that would be given information, the direction vector for the line. So let's multiply the top and bottom by the magnitude of v, that is the direction vector for the line. Multiply the top, multiply the bottom. So I haven't changed it. And the reason for doing that is that now what I have here is the magnitude of the cross product of these vectors PQ and V. Magnitude of PQ cross V. Cross products are always vectors, and so I'm using magnitude, not absolute value, but actually the magnitude of that cross product, and we'll do that in a minute. And I still have to divide by the magnitude of V. So this is how I calculate the distance, is finding the vector PQ, identifying the direction vector, doing the cross product, getting the magnitude, finding and dividing by the magnitude of V. So let's do that. So maybe we go back and say, what is PQ? It is any point on the line to this target point to which I want to calculate distance. And so maybe I can squeeze it in right here. What is vector PQ? PQ as a vector, the kind of convention that I'll follow is this is initial point P, terminal point Q. And so to put it in the component form, I need to take each of the endpoints, each of the components of the terminal point, and minus those values components of the initial point. So 3 minus 3, 2 minus 4, and 4 minus a negative 1. That gives me the vector PQ. And I have vector V here. So let's put this together. In order to get the distance, I need to get PQ and V, the direction vector of the line, negative 2, 5, 1. Take a cross product of those. The way I do cross products typically would be if I need to get the components of the cross product, the actual vector form, I use I, J, and K on the top row of a table. Then this really does matter, because the order in which you do the cross product actually produces a slightly different result. So you need to put the initial vector as your second row, and then the vector that's second here in the product, put that last. Now this is a 3 by 3 determinant. The way I like to do that is I'll put I first, because it sort of helps me in the order. And another thing is that this is a bunch of arithmetic that is so easy to mess up on, that I found a routine that works for me where I will do the I component, and then what I'll have to do is multiply negative 2 times 1 minus 5 times 5. And I write out that part at that stage without trying to do any more in my head, because I'll mess it up. Part of the definition of the cross product is always going to be a minus here. I'm doing a 3 by 3 determinant, so that's part of that process. So then for the J, now I block out this column, and I block out that row, and so it'll be a 0 times 1 minus the 5 times the negative 2. And I don't try to go any further in my head than just that, right? So let me say one more time. I think I didn't really say it. If I have the component I, the first component, I block out that column, block out that row, and multiply this negative 2 times 1, and then minus the 5 times the 5. And then I block out the J and do 0 times 1 minus 5 times negative 2, and then this always has to alternate, plus, minus, plus, the K component. And now when I block out the column and row on which I have k, then I have to do this 2 by 2 determinant, 0 times 5, which is 0, minus negative 2 times negative 2, which is 4. So this is negative 27i. That's a 10 and then a minus, so I have a minus 10j. So yeah, there's just arithmetic, but it's tempting to go fast and then very likely to make an error. So then I have minus 4 times k. So this is the cross product, but what I need in this formula for distance is the magnitude of the cross product. So finding the magnitude, I get 845 when I add that up. And so now I can go back and actually compute the distance from the formula that I derived. Magnitude of the cross product divided by magnitude of the direction vector. This was square root of 845 over, and this magnitude of v I didn't actually compute. Let's go back and find the magnitude of v. It's 4 plus 25 is 29 plus 1. That's square root of 30. Now, we could go to a decimal value because it might be a practical answer, but typically, unless it's a word problem, what I'm really looking for on the exams would be an exact value for some pure mathematical question, right? So to get an exact value here, now what I could do here is that it's certainly there's a 5 that I can cancel with these guys. So let's see where that goes. So we got 845 over 30, and we could reduce this guy, right? It actually reduces to 169 over 6, which does produce a simpler expression that's still exact, right? So we got square root 169 over 6, and that means you actually have 13 over root 6. Now, that's a pretty good answer. Simplified, it doesn't necessarily have to be rationalized, although in this case, it's pretty easy to rationalize, and so that's a good thing to do as well. You multiply top and bottom by square root 6, and you get this. Okay, so again, like an exact answer, typically what I'm looking for when it's a just pure mathematical question, more inclined toward getting decimal values if it was a word problem where a more practical answer might be more valuable. Okay, so let's move on and tackle this other kind of distance question where we have the distance, to find the distance from the plane, from a plane, let's say this particular plane 3x minus 2y plus 2z equals 6, to this arbitrary point 1, 5, negative 4. How do we find the distance from the point to the plane? So again, a perpendicular to the plane would be the shortest distance, and that's what we're trying to find. Let me see. I've got another, I put this into Mathematica also. I've got my equation there in a window. I've got another ball at this point, 1, 5, negative 4, that has this radius. And so and here's a picture of it. And so we can imagine now this point floating in space, and we're trying to calculate that distance to the plane. So really just the height of that point above the plane. So this is an example where we can use the dot product and the projection formula that was derived before to find this particular distance. So again, I'm going to do some derivation to go back to using a projection to explain where the formula comes from. If you're answering this on a test or a homework, you go right to the formula and just calculate the answer from the formula. Let's say so the principle that I'm using is that I will need to identify a normal vector, to the plane, and I'm also going to need a vector that points from any point on the plane to the point that I'm trying to calculate a distance to. So let's call this point P, kind of following could call it anything, but to follow what I was doing before, this one we could call Q, kind of a target point to which we want to find distance. And let's find any point in the plane and call that point P. And now, of course, you can draw the normal vector anywhere, right? This vector can be drawn anywhere. I'll leave it here for now. And those are the pieces that we'll use to answer this question. So maybe one key thing to notice is that the normal vector that is perpendicular to the plane can be read right from the equation. The normal vector is going to be 3, -2, and +2. And so this calculation will be figuring out basically really this distance here. Right? This is the distance that I'm trying to find. That's the distance d. That's the distance from the point to the plane. So maybe I'll do this. What I'm trying to do is find a projection of PQ onto n. So there's the distance I want to find. So it is exactly the projection of PQ onto n, and you can maybe either I'll explain it by moving this normal vector and seeing the projection of PQ onto n. Projecting PQ onto n would find that distance. Or maybe we just see it this way, that the distance is in fact just the result of projecting onto n this vector PQ. So to find what I really need is just the scalar value of that projection of PQ onto n. So it's the scalar of the projection of vector PQ onto n. It's the magnitude of that projection. We'll just get to the point that the actual magnitude of that projection is PQ dot n over just the magnitude of n one time, right? In the actual projection vector, you would have had n factorial over magnitude of n, and that's where that square comes from. But this creates a unit vector in the direction of n. This is the scalar that you multiply times that unit to actually get the length of the projection. So in fact, it's just this guy that is the magnitude, right? And that's all that d is. It's the magnitude. It's the scalar part of the projection of PQ onto n. And important also, the dot product could be negative, so the magnitude is an absolute value. You notice I'm just using one bar to indicate absolute value of that dot product. This is the magnitude of that projection. So these are the things that we'll need to figure out. What's the vector PQ, what's the vector n, and get a dot product, take absolute value, etc. All right, so we'll do something similar to find PQ. So a piece of this will be, what exactly is this point that's in the plane? Now, what that would be is any point that makes the equation true. So you could pick any two of these variables to be 0 and solve for the third one. And I think what I'll do is go 0 and 0 for x and y, and the z value would have to be 3. So I'm going to go with 0, 0, 3 as my choice. The interesting thing was that there are infinitely many choices, and all of them would work. Right? For example, you could go 2, 0, 0, or you could go 0, -3, 0, and all of these points would work. Any point that's on the plane would work. So I'll choose 0, 0, 3. So then I still need to get the vector PQ. So let's see, where could I fit that in? Terminal points Q, so it's going to be 1 minus 0, 5 minus 0, and -4 minus 3. Okay, so there I have the point 1, 5, the vector PQ is 1, 5, -7. This right here is vector PQ. And I've already got the normal vector off the equation. 3, -2, 2. And I'm calculating that distance d using this formula for the value of d. So then we could say the distance is the dot product of PQ dot n in absolute value. Don't forget absolute value. Distance has to be positive, and it has to be the magnitude of that projection. So we've got 3 plus 5 times negative 2, that's a negative 10, plus negative 7 times 2, that's a negative 14. That's 9 plus 4 plus another 4. So this is negative 21 in absolute value over the square root of 17. Alright, so that's good. That's the answer. It's a tradition to rationalize, and it isn't too difficult to do it again in this case. So let's just say 27 root 17 all divided by 17. It does look better that way, but both of these are correct. Alright, so we have reached the end of the video. That's it. I hope that it was helpful.